Hi again, we have been discussing Hamiltonian dynamics. Today we will solve a few problems using the techniques that we studied so far. And the first question is this is a question which was asked in one of the previous examinations. If the Lagrangian of a particle moving in one dimension is given by L equal to x dot square divided by 2x minus v of x, then what's the Hamiltonian? The question is, what's the Hamiltonian, right? So you know how to find the Hamiltonian from the Lagrangian. Of course, you should do x dot p minus L, h equal to x dot p minus L, right? This we can say this will be a function generally of x dot p and x, but we should get rid of all x dot in terms of p. We know, we should get rid of all x dot in favor of p. Right, you know how to do that, but we said that some of the problems can be simplified further by writing simply h as t plus v. Right? When can we do that? There were two conditions. The first condition was that the transformation equations should not involve time explicitly. The second condition was that we shouldn't have a velocity dependent potential. Right? So here you see that both these conditions are satisfied. Here there are no transformation equations which depend on time explicitly. Also, the potential here does not depend on velocity. So we can simply write the Hamiltonian as t plus v. So we start by writing the energy function, will denote it as small h, the energy function as t plus v. Okay, so in this case that becomes x dot square divided by 2x plus v of x. Right? Is this the Hamiltonian? No, this is not the Hamiltonian because this is a function of x dot. Okay. The Hamiltonian is a function of p. It cannot be a function of x dot. So what should we do? We should get rid of this x dot in favor of p. How do we do that? We find p is equal to dou L by dou x dot, right? In this case, that's equal to 2x dot divided by 2x, which is nothing but x dot divided by x. So from here we see that x dot is equal to xp, x dot equal to xp, right? Now we just substitute this in here in the energy function and we have got the Hamiltonian. Okay, h is equal to, it is x square p square divided by 2x plus v of x, and that's half p x square plus v of x, which is option A. We've got the answer. Okay. Now, if you have a doubt, this is the quickest way of solving these kinds of problems. If you have a doubt as to whether this h equal to t plus v is valid, always go for the traditional method, all right, or the the method which works everywhere. We can write x is equal to x dot p minus L. Okay, you find p from this Lagrangian and get rid of all the x dot in the final expression and you will have the Hamiltonian. Okay. Alright, so that's the way I have solved it in your notes, so you can check that. It's easy, you should practice both these methods. Okay, but in a competitive examination, it will save you a lot of time if you immediately know that Hamiltonian can be written as t plus v. Okay. So here we have a different kind of problem. This also was asked in one of the previous NET exams. The Hamiltonian of a simple pendulum consists of a mass m attached to a massless string of length L. Right? The Hamiltonian is p theta square divided by 2ml square plus mgl 1 minus cos theta. Right? Now, if L denotes the Lagrangian, what's the value of dl by dt? Right? You are asked to find the value of dl divided by dt. Right? How do we go about this problem? Okay. So we know that in this case there are just there's just one dimension. Okay, it's theta. So we can write h is equal to theta dot p theta minus L. All right. So from here we see that L is equal to theta dot p theta minus h, right? Or generally, okay, we can say that h is equal to summation over I qi dot pi minus L, or this means that L equal to, you can also use this relation to find the Hamiltonian from the Lagrangian. All right, so here we see that L is equal to h minus, it's summation I qi dot pi minus h. Okay, that's a Lagrangian. So you should be careful. Usually the Hamiltonian is only a function of what is a q, p and t. Alright, and the Lagrangian you should write it always as a function of q dot and t. All right. So here in the Hamiltonian, the functional dependence is q pt, whereas in the Lagrangian, the functional dependence is q dot t. Right. So, but in this problem, all right, so in a competitive examination where you have multiple choice questions, all right, it's always a good practice to go look at the options, all right, because sometimes the options will give you a hint as to the easiest way to proceed, right. So, if you look at these options, right, in this case, if you look at these options, you see that there is this p theta, theta, p theta, theta, p theta, theta, p theta, theta, all right, in all the answers, all the answers are given in terms of p theta and theta. Okay, there are no theta dots. That's my point. There are no theta dots in the answer, right? So this means that when we do this, right, when we start solving this problem, we don't have to write the Lagrangian as a function of theta and theta dot, right? Because in order to get one of these options, we shouldn't have any theta dot in our answer. So it's a good thing because we have this hint, and from the beginning we can get rid of theta dot in our formulation. Okay, that's how we will proceed. Yeah, I hope that's clear. Now, how do we do this? We have got the Hamiltonian, all right, and the Lagrangian, as I said, is p theta, theta dot minus h, all right, and now we anticipate something, all right, we anticipate something because we are asked to find dl by dt. We are asked to find dl by dt. Am I right? So, when you find dl by dt, we said that we will write a Lagrangian as a function of theta, p theta and t, let's say, all right, because usually you should remember that Lagrangian is not a function of p theta, it's theta, theta dot and t, but for our purposes we said that it's convenient because looking at the options we say that it's convenient writing a Lagrangian as a function of theta, p theta and t, right, and when you find dl by dt, okay, when you find dl by dt, you will certainly encounter terms theta dot and p theta dot, am I right? Right. So, when you find dl by dt, you are going to encounter terms theta dot and p theta dot, right. So, let's anticipating this, let's already find theta dot and p theta dot. Okay. So, theta dot using the Hamilton's equations is dou h by dou p theta, which is simply p theta divided by ml square. You just find dou h by dou theta, right. This is in anticipation, right. P theta dot, not yeah, p theta dot is equal to minus dou h by dou theta, that's minus mgl sin theta. Okay, these things are just Hamilton's equations and we have got them. Right. Now we will find the Lagrangian. Lagrangian is equal to p theta theta dot, but we don't need any theta dot. So immediately we write this theta dot in terms of theta dot as we obtain from the Hamilton's equation. So it's p theta and theta dot is p theta divided by ml square, okay, minus L and the Lagrangian, right, the Lagrangian, sorry, minus h, the Hamiltonian is just this, it's p theta square divided by 2ml square plus mgl 1 minus cos theta, right. We are finding the Lagrangian, this is the Hamiltonian. Okay, it's fine. Now we have got our Lagrangian in terms of p theta and theta, right. Again, I emphasize that this is not the correct form of the Lagrangian, but we took a hint from the options given, right. We took a hint from the options given, right. Otherwise, you will see that you will go through unnecessary complications and lengthy steps doing this, right. Now, it's just a matter of finding dl by dt. Okay, you can find dl by dt now, it's not very difficult. So, one way to do that, okay, you can either differentiate this thing, right, you can either differentiate this thing dl by dt, or we know that dl by dt is equal to dou L by dou p theta dot, because we have written our Lagrangian, right. In this case, we have written our Lagrangian as a function of theta and p theta. This means that dl by dt, see, there is no explicit dependence on time. So, dl by dt is equal to dou L by dou p theta dot plus dou L by dou theta dot, right. Of course, we don't want this theta dot, we will write theta dot as p theta divided by ml square. Okay. All right. So, that and what's this dou L by dou p theta? What's dou L by dou p theta? We already found dou L by dou p theta, that's p theta divided by ml square. Okay. And p theta dot, that also we have found, right. We need dou L by dou p theta, we have found it. We have also found p theta dot. P theta dot was just what did we find for p theta dot? P theta dot is just minus mgl sin theta. So, these things we have here, right? So p theta dot equal to minus mgl sin theta, dou L by dou theta is minus mgl sin theta. These are just fine, all right? So once you know to write it like this, once you write this like this, the rest just follows, because we know how to find dou L by dou p theta and dou L by dou theta. We also have already found p theta dot and theta dot. So it's just a matter of substituting these things back into this equation to get the correct answer. Okay, so you can just put it in and substitute. You do the steps by yourself and the final answer will be this, right? Of course, there are other ways to do that. I think you should really try to solve it in some other method, all right? Of course, when we study the Poisson brackets, we would be, we'll try to solve the same problem using Poisson brackets also. Okay, so there are different ways which can be used, all right? Okay. Here is another problem. A particle of mass m and coordinate q has the Lagrangian half mq dot square minus lambda by 2 qq dot square, all right? Where lambda is a constant. The Hamiltonian for the system is given by, okay, you need to find the Hamiltonian, right? Of course, you can find the Hamiltonian as qq dot minus L. Okay, we have only q and q dot, so it's qq dot, it's pq dot minus L, I'm sorry. You can find the Hamiltonian as h is equal to pq dot minus L, and you know how to find p, etc. All right. But as I said earlier, we have an easier way to do it if there are no velocity dependent potential, and if there are no transformation equations involving time explicitly. You can always write Hamiltonian as t plus v. Okay, the question is, can we write in this case h is equal to t plus v? All right. The answer is yes. Why? Because you see that there is no potential energy term here. Now, how do you identify whether a term is potential energy or kinetic energy? So, the kinetic energy, all right, you can identify the kinetic energy in that the kinetic energy will be quadratic, okay, quadratic in, let's say, generalized velocities, okay, generalized, or simply in velocities. Okay, it has to be quadratic in velocities, all right. So, in this case, you see that you've got a q dot square here and a q dot square there, okay. So, this means that this whole term is the kinetic energy. There is no potential energy term, and of course, you can write h equal to t plus v, which in this case is simply t, all right. So, this we can write for simplicity q dot square multiplied by half m, or simply we can take q dot square by 2 outside, I think, and it's m minus lambda q, all right. So, this is our Lagrangian, it's q dot square by 2 multiplied by m minus lambda q. Right. Now, this is simply a kinetic energy term, so you can write h equal to q dot square divided by 2 m minus lambda q. What's the next step? You don't need this q dot square here, you need to write it in terms of p. Okay, so how do we find p? How do we find p here? Sorry, q dot square by 2. How do we find p here? You can find p by taking dou L by dou q dot. That you can find p by taking dou L by dou q dot. That's what we have done here, and from here you get q dot is equal to p divided by m minus lambda q. Okay, it's not there's nothing particularly difficult here. The only thing here is that now you substitute for q dot in terms of this p and you will get the final answer. Okay, yeah, let's do this. Okay, so we have got so the Hamiltonian would be p divided by m minus lambda q, there's a whole square because it's q dot square, okay, multiplied by, there's 1 by 2 here, m minus lambda q. So, you see that there's m minus lambda q that can be cancelled here. Okay, there's a square there. So, that becomes p square divided by 2 m minus lambda q. That's the answer. Okay, this is the quickest way of doing it, and you should really try doing it in both ways. You should be familiar to you should be able to use both methods. You should get some practice in finding the Hamiltonian in both methods, and in your notes I have given the other method. All right, so you can go through that. If you have any questions, you can contact me. So, what answer do we have here? What answer do we have here? It's p square divided by 2 m minus lambda q, and that's option B. Okay, that is option B. Right. Here is another Lagrangian. Okay, I am not going to solve this problem in detail. This is an exercise for you. You try to solve it without looking at the solution, right? You try to solve it without looking at the solution. Okay. Now, if the Lagrangian, I'll just give you the general idea here. If the Lagrangian of a dynamical system in 2 dimensions is L equal to half mx dot square plus mx dot y dot, then what's the Hamiltonian? All right. Now, again, the question is, can we write h equal to t plus v here? Okay. The answer is, of course, yes, because if you look at this, you see that there's an x dot square term here and an x dot y dot term here, right? Both these terms are quadratic in velocities. All right, we have got x dot square and x dot y dot. Okay, these are quadratic in velocities. Okay, this means that this whole term is kinetic energy alone. All right, so the trick in a competitive examination is to identify that this indeed can be written in the form t plus v, because if you do that, you can skip a lot of steps. Right, so from here it will get a bit tricky because when you find the momentum, etc. But here this answer is simple. You can write the h function as half mx dot square plus mx dot y dot. All right, this is the h function, and in order to find the Hamiltonian, you should get rid of x dot and y dot in favor of what do you say, px and py. Okay, for that you have to find px and py from the Lagrangian, which is easy. You can try to do that. Okay, you see that there's a little bit of subtlety here, because when you find px, you see that it's mx dot plus my dot. All right, it's mx dot plus my dot, whereas py is simply x dot. Sorry, py is simply mx dot. Py is simply mx dot. All right, so you have to, here it's mx dot plus my dot, so you have to solve between these two equations to find x dot and y dot in terms of px and py. All right, it's nothing serious. You can go through that, and as I said, if you have any questions, you can ask. This is left as an exercise for you. Okay. All right. So the only thing that you need to be careful here is that you need to, when you find px and py, okay, you need to solve these two equations to obtain x dot and y dot in terms of px and py here. That's only subtlety here, which is not very difficult. Okay, we can do that. The final answer is option C. I think you can check. All right, it's px py divided by m minus py square divided by 2m. The next problem, the Hamiltonian of a system with generalized coordinate and momentum. Okay, again we have a one-dimensional system here, is h equal to p square q square. A solution of the Hamiltonian equation of motion is, okay, you need to find the solution to the Hamiltonian equation of motion. All right, now by looking at the options, right, you see that p is equal to some function of t and q is equal to some function of t. All right, so what you are supposed to find by solving is q of t and p of t. All right, how do we go about this? We construct the Hamilton's equations, whereby you will get q dot and p dot. Okay, now these are differential equations. Okay, you can find it from the Hamilton's equation of motion. These are differential equations and you have to solve them. Okay, that's all, simple. Okay, but there's a small issue here. When we attack these kinds of problems, we have to be a bit careful, right? Because generally the functional dependencies can be q, p and t. All right, so when we talk about these things, okay, when we try to solve these equations, the equations may involve q, p and t. All right, so depending on the situation, you may have to eliminate one of this. All right, we need, for example, in order to find q of t, you need an equation for q dot which depends only on q, or only on q and t. Okay, so in order to, we'll find q dot. Okay, I'll explain this in more detail, but the thing is that we can find q dot from the Hamilton's equation, we can find p dot. Okay, but we may not be able to immediately solve it, because this q dot can be a function of q, p and t. All right, so what we need to do is that we have to get rid of this p in this case. All right, if there's a p dependency, we need to get rid of this p dependence and write it simply as q dot of q comma t. Now we can easily solve it. All right, so that's the only extra step that will be necessary. All right, so in most cases, so if you are talking about phase space trajectories, which we will deal with in some later, in that case you may have to find q of p or p of q. All right, in that case it may be convenient to eliminate the time term. Right. So let's see, you will see how this works in this problem, right? So your Hamiltonian is q square p square, which means that q dot equal to dou h by dou p, which is 2q square p. No problem, it's just dou h by dou p. Alright, so you have got q dot equal to 2q square p, which means that dq by dt is equal to 2q square p. Alright, now in order to find q of t, you just have to integrate this, except you see that this is a function of q and p. Right, so it's not easy to integrate. So you need to eliminate this p here. So how do we do that? So let's stop there and let's find p dot. So when you find p dot, you see that it's minus dou h by dou q, and that's minus 2p square q. So from here you get dp by dt is equal to minus 2p square q. Okay, dp by dt is equal to minus 2p square q. Alright, so in order to eliminate one of this, alright, so here you see that dp by dt is a function of p and q, dq by dt is a function of p and q. Right, so in order to eliminate, you divide one equation by the other. Alright, so you can find, in this case it's easy, you can find dq by dp. Alright, it's just dividing this equation by this equation. Alright, you will see that. If you do that, you see that dq by dp is minus q divided by p. Right, dq by dp is minus q divided by p. Alright, now this means that you can separate the variables and write dq by q is equal to minus dp by p, just separating the variables. Alright, now you integrate on both sides, you will get log q is equal to log p. Okay, plus there will be some constant. So there's a minus here. So log p is equal to minus log p, and then there will be a constant. Alright, or together you can write log q plus log p is a constant. Alright, this means that log of qp is a constant, and this means that qp is a constant. Okay, now by integrating this, you find p as a function of q. Alright, that's the trick that we are using here. So the thing is that, I'll explain again. Once we obtain this dq by dt, you see that there's this q and p in here, right? When you find dp by dt, there's a p and q in here. Alright, but in order to find a correct differential equation and solve it, you need q of t, alright, or q dot as a function of q and t alone. Alright, only then you can directly integrate it. Okay, so here you see that this dq by dt has a p dependence and this dp by dt has a q dependence. Alright, so you have to eliminate one of this. How do we eliminate this? If we can find p of q, or p as a function of q from these equations, then you can substitute it here, and then you will get dq by dt as a function of q and t alone. Alright, I hope that's clear. So for that, so we need to find q as a function of p. So in order to find q as a function of p, we eliminate t from these equations. Right, we eliminate t from these equations, so you will get dq by dp. Right, now there's no time term in this equation. You can solve this and find q of p. Okay, now once you find q as a function of p, you can substitute that back here, and then you will get dq by dt as a function of not q of p, p of q. If you find p of q, for example, or q of p, it doesn't matter, you can substitute that here, and then you can get an equation dq by dt is equal to 2q square, and then some function of q itself. Okay, some function of q itself. Alright, now you will get a nice differential equation and you can solve it. Okay, so there are a few steps involved in here. So the trick in trying to solve such equations is always to eliminate one of the three. All right, there are three variables that we are interested in here, so you always have to eliminate one of the three. Right, so first we eliminate t term and write q of p. That's exactly what we did here. We found p as a function of q. All right, p of q is equal to k divided by q. All right, now we got p as a function of q. Now you can eliminate this p in here. All right, so you simply write p is equal to k by q. So dq by dt will become 2qk. Hope that's clear, because you substitute for p here, it's you get q dot or dq by dt. dq by dt is equal to, what's it, 2q square. Okay, and instead of p, you substitute it in form of the simple function k divided by q. Right, so it's 2qk. Now it's easy to integrate this because you can separate the variables. So dq by q, you can write dq by q is equal to 2k dt. Alright, now you can integrate it. Integral dq by q is log q, as you might already know. So log q is equal to 2kt plus log c, that's a constant. Alright, 2k is a constant, so integrating is simply 2kt. Alright, so you write this for convenience as log c. From here you see that q is equal to c e raised to 2kt. So once you find q, you can find p, because p is equal to k by q. Right, so p is equal to k divided by q, so it's k by c e raised to minus 2kt. Right, now you can look at these functional dependencies. Q is e raised to 2kt and p is e raised to minus 2kt. Okay, there are constants there, and you look at the options. Okay, you see here p is minus 2 kt, something 280, and q is 280. Right, so here p is minus 280 and q is also minus 280. Here it's p is like it goes like e raised to 80, e raised to minus 80. So you see easily that this is the correct answer. Okay, so in an examination you should be able to identify the correct answer by inspecting. Okay, so you can easily show that. Okay, the results that we obtained here in terms of k and c can easily be written in form of option A. Alright, but just by looking at the functional dependencies here, we can eliminate all other possibilities and not worry about the constants. Alright, so that's the way you solve this problem. Okay, now get some practice with this. You will be asked to solve more problems. Okay, so the trick, again I repeat, the trick is to eliminate one of the three variables. Alright, in this case first we eliminate t in order to find q of p, and using q of p we eliminated p from this equation. Alright, then we got a nice differential equation, dq by dt is equal to 2qk. Alright, now we have eliminated p from this. The only variables appearing here, the only things that appear here are q and t. Now we can easily solve this, you can easily integrate it and obtain the final answer. Okay, so I think we'll stop with that, or maybe we'll do one more problem. Okay, let's do one more problem. Right, the Hamiltonian corresponding to a Lagrangian L equal to ax dot square plus by dot square minus kxy. Alright, okay, I'm not going to do this, it's an exercise for you. Okay, again you may identify that you can write the Hamiltonian as t plus v. Alright, this is the potential energy term, so you can write as t plus v and then substitute or get rid of x dot and y dot in favor of px and py. Okay, so it's left as an exercise for you. You can solve it. The solution is given, but I ask you to solve. I ask you to solve the question or do the exercise by yourself without looking at the solution. Alright, only then you will know where you may go wrong. Alright, if you look at the solution given here, all the things may look quite obvious. Okay, and you may not really understand where you may go wrong. So it's important that you try to solve these problems without looking at the given solutions. Okay, so with that I'll conclude this session. Thank you. In the next session we'll solve a few more problems from the Hamiltonian formalism, especially those asked in the previous NET JRF exams. Okay, all right, thank you.